You know, when you think about it, everything is in motion, from a tiny snail to our entire planet whipping through space. But how do we actually talk about it? How do we measure it? Turns out there's a whole language for it, and today we're going to learn how to speak it.
Okay, first up, take a look at this thing. This is the Bloodhound SSC. And yeah, it looks like a car, but it's really more of a rocket ship on wheels. Seriously, it's a hybrid of jet and rocket tech, and it was built for one single absolutely bonkers goal: to go faster than anything else on the ground, ever.
So what's the target? Get this, 1,600 kilometers per hour. I mean, that's literally faster than a speeding bullet. It's one of those numbers that's so huge, your brain kind of struggles to even picture it, right?
So how do we even begin to wrap our heads around a speed like that? Or, for that matter, the speed of an Olympic sprinter? Or, heck, even your morning bus? Well, it all starts with the basics. We need the right tools, the right words. We need to learn the language scientists use to describe any journey, big or small.
All right, so let's dive right in. What is speed, really? Let's start right at the beginning.
Okay, at its heart, it's actually a super simple idea. Speed is just how much distance something travels over a period of time. That's it. It's just a way to measure how fast something is moving. And to see this in action, I mean, the contrast here could not be more extreme. On one hand, you've got a snail, inching along, covering a teeny tiny distance every second. So, super low speed. On the other hand, a cheetah. In that same second, it covers a massive amount of ground. And that means, you guessed it, an incredibly high speed.
And you see this everywhere, right? Think about walking. You're maybe moving a little over a meter every second. An airplane? It's blasting through the sky at 250 meters in that exact same second. It's a totally different scale, but the idea is identical. It always comes back to that simple idea: distance over time.
So, here's the bottom line. It's a really simple relationship. The faster something moves, the higher its speed. That's it. That's our first absolutely crucial building block for understanding the language of motion. Okay, so we've got the general idea down. But what about the numbers? How do we get, precise? Well, for that, we're going to need a little bit of super simple math.
And to make this real, let's talk about the fastest human ever. Yeah, I'm talking about Usain Bolt. We've all seen the highlights, but have you ever wondered how fast was he actually going when he set that insane world record?
Well, to figure that out, we use this beautiful, simple little formula. Average speed is just the total distance you've gone divided by the total time it took you to get there. Simple as that.
So, let's do the math for Bolt's record. Okay, step 1, the distance. That's easy. It's a 100-meter dash. Step 2, the time. And what a time it was. 9.58 seconds. All we have to do now is divide that distance by the time. 100 divided by 9.58.
And boom, there's our answer. 10.4 meters per second. That's how fast he was moving, on average. Think about that. For just under 10 seconds, that was the peak of human speed. And we can put a real number on it, all thanks to that simple formula.
All right, so we can define speed and we can calculate it. That's awesome. But what if we could, see it? What if we could turn a whole journey into a picture? Let's check it out.
Okay, we're going to use a super simple, everyday example here. Imagine a bus traveling between two stops. They're 450 meters apart, and we're just going to track its progress.
Okay, first checkpoint. After 10 seconds have passed, our bus has traveled 150 meters. Let's just, mentally put a pin in that spot.
All right, another 10 seconds go by. So at the 20-second mark, the bus has gone another 150 meters. It's now 300 meters from the start. That's our second pin.
And finally, at 30 seconds, it pulls into the second bus stop. It's traveled the full 450 meters, and now it's stopped. That's our last data point for the moving part of the trip.
So what do we do with those points we just collected? Well, this is where the magic happens. We can plot them on a graph. We put time along the bottom and distance up the side. When we connect those dots, we get this, a picture of the entire journey. This is what we call a distance time graph, and it's incredibly useful.
And believe it or not, this graph tells a story. See how the line is going up? That just means the bus's distance from the start is increasing. In other words, it's moving. Now, if the line was steeper, that would mean it was going faster. And what about a flat, horizontal line? Well, that means time is ticking by, but the distance isn't changing at all. The bus is just sitting there, completely stationary. So there you have it. We have our tools now, we have a definition for speed, a formula to calculate it, and even a way to draw a picture of it. Let's wrap this all up.
Because here's the really cool part. The exact same ideas we just used for a simple city bus, well, they apply to basically everything in the universe. Take our own planet, Earth. It's hurtling around the sun at an incredible 30,000 meters per second. And yeah, we could plot that on a distance time graph too. We need a much bigger sheet of paper.
And that right there is the big idea. This isn't just about runners and buses. This is it. This is the universal language science uses to describe motion, whether it's a snail or a person or an entire planet.
So now you have the tools. You speak the basic language. You can figure out the speed of a car on the freeway, a plane overhead, even your own walk to the store. So I'll leave you with this question. What's the first journey you're going to analyze?